Alright, this video is going to describe solving systems of linear equations. I'm going to cover the three main methods we have, which are graphing, substitution, and then addition and elimination. Before I get started there, I'll describe a system and talk about solutions that we know so far. So here we have a system of linear equations, and what that means is just we have two or more linear equations, each of which individually have infinite solutions. I did some work here and I found 4 solutions for each of these, and I just want to write these down real fast to remind you about these solutions. I found these solutions: -1 for x, 0 for y, 0, -2, -3, 4, and 1, -4. And you can spend time verifying that. And again, if I plug these values in for x and for y and do the math, the arithmetic, these should work out both sides to be equal. The second equation also has an infinite number of solutions. I'll list some of them here. Again, starting with the asymptotes, plugging in 0 for one of the values is always the easiest. And then a few others just to make it interesting. Alright, so those are tables of values for each of these linear equations. And again, that's not the comprehensive list, that's just a list of 4 of them for each. Importantly, to talk about what the solution to the system is. The solution to the system is the solution to a system of linear equations is the one solution that works for both of them. And not by chance, I have that here actually. The solution to the system, as we'll see in all the methods we're going to be talking about today, is x equals -3 and y equals 4. And why that is because that pairing works in both of those equations. And that's the important part. This is the one set of values for x and for y that if I plug it into either of these equations, it works. Alright, what I'm going to talk about now is often the first method that we talk about solving these, not because it's the most efficient, but because it's it makes the most sense usually. I'm going to talk about graphing these equations. First of all, I'm going to graph this first one. I could put this in slope-intercept form, but since I already have some solutions here, I'm just going to graph it based on that. So I'm going to graph these intercepts. So I have 0, or -1, 0, and 0, -2. That gives me a line that looks something like this. And then if I graph the other equation, I'll plot a few of those points: 0, 3. And 9, 0. Again, I'm using my intercepts here to graph, and let me put in that line. And it's important to remember what these lines or the graphs of these equations represent. These equations or these lines represent all of the solution to these equations visually. And again, if you pick any point using these intercepts that I have chosen, or the values that I have in my table of values, they all lie on this line. In fact, every point on this line represents an x and y value, which is a solution to the equation. The same is true for this red line, the second line. I plotted it with these 2 points, but all of the other equations, 3, 2, all the other solutions, are on this line. Again, this line represents all of these solutions to this equation. Therefore, the one place where they cross, or the intersection of these two graphs, is the solution to this system. And again, this right here is at -3 on the x-axis and 4 on the y-axis. And that gives us our solution over here again of x equals -3 and y equals 4. The issue with this method is if you aren't very good at drawing lines, to get an accurate answer, it's going to be very, very difficult. Let's talk about the 2 other algebraic methods for solving these systems. Substitution is the first method we'll talk about, which is an algebraic method for solving these. And just to recap real fast, each of these have infinite solutions. We can't solve for x or for y separately to get a value in either one of these because we have a 2-variable equation. But we can interact both of these and actually get a solution for x and for y separately. Let's talk about how to do that. So what substitution says, you take one of your equations, and I'm here going to take my first equation, this 2x plus y equals negative 2. And what I need to do is solve this equation for one of the variables. It doesn't matter which variable I solve for, but things can be easier. And it's always kind of a choice of one is easier to solve for than the other. In this case, what I'm going to do is I'm going to solve this equation for y. My main reasoning there is because there's no coefficient in front of y, so I'm not going to have to divide by anything to make messy fractions. And so to do that, what I'm going to do is I'm going to subtract 2x from both sides of this equation. And what I'll get is y equals negative 2x minus 2. Okay, that's the big first step for substitution. The second step that I do is I'm now going to substitute this value of y, or this expression, negative 2x minus 2, into the other equation. So I have my other equation, which is x plus 3y equals 9. What I'm going to do is I'm going to replace this y in the second equation with the equivalent expression equal to y above here. Here's what that will look like. I'll have x plus 3 times y. Now y is negative 2x minus 2. And that equals 9. That right there was the substitution method being employed. Why that's useful is now I have an equation with just x's, and now I can solve for x in this equation. So I'm going to distribute this 3 through to get negative 6x minus 6 equals 9. Combine my like terms here, 1x and negative 6x is negative 5x. Minus 6 equals 9. I'm going to add 6 to both sides of this equation to get negative 5x equals 15. And then I'm going to continue up here, and I get, so negative 5x equals 15. Divide both sides by the negative 5. And what I get is x equals negative 3. All right, that's a big step, and that's the same value for x that we had in the other method of graphing. Importantly, hopefully you're realizing that, oh, I only have my x. How do I find my y value? Well, I take this x equals negative 3, and now I can plug it into either one of my original equations. It doesn't really matter. In fact, usually the easiest one to do is to use this version of the first equation because it's already set equal to y. And so here we go. I'm going to say y equals negative 2 times x, which is negative 3, minus 2. And all I need to do is simplify this side. And there you have it. So my solution for this equation using the substitution method was x equals negative 3 and y equals 4. Again, this is called an algebraic method because I'm using algebra steps to solve this, opposed to the graphing method previously. I'm now going to discuss the addition elimination method, which is a whole nother method for solving this system. All right, the addition elimination method. The addition elimination method introduces a new concept, that you actually can put these two equations together through addition. I'll just show you real fast what that looks like. So if I wanted to add these two equations, I just got to make sure my variables are lined up and my constants are lined up. And when I add them, I get 2x plus x is 3x. And then 1y plus 3y equals 4y. And negative 2 plus 9 is 7. This right here is a third true equation that I've gotten through the combination of those other two equations. That said, that's not really useful at this point, and I'll show you what I mean by useful. What we're going to do is when we use the addition elimination method, what we want to happen, well, is the second part of the name, we want things to eliminate when we add them together. And we do that by multiplying an equation on both sides by a constant. In this case right here, what I'm going to decide to do is to eliminate the x's. What that means is when I add these together, I want there to be 0x. But obviously when I added them together originally, I got 3x. Well, how can I do that? Well, I'm allowed to multiply both sides of any equation by any number I want. What I'm going to do is multiply the second equation by negative 2. I'm going to multiply all the coefficients in that equation by negative 2. I'm going to write that result here right underneath. So I got this 2x plus y equals negative 2. Now the second equation is going to, everything's going to be multiplied by negative 2. I get negative 2x minus 6y equals negative 18. And again, I have exactly the same system. I've just made this second equation a little bit different by multiplying all the coefficients by negative 2. Why I did that is by what's going to happen when I add these together now. I get 2x plus negative 2x. Those end up canceling each other out and give me 0 x's. I have 1y plus negative 6y is negative 5y. And then negative 2 plus negative 18 is negative 20. This is an awesome equation, again, because what I have now is an equation with just one of the variables, in this case just y, and I can solve this equation for y by simply dividing both sides by negative 5, and I get y equals 4, as I had expected. Though, in any of these methods, I need to find my second variable. I know y equals 4. I did that through addition and elimination. What I'm going to do now is I'm going to use either one of the original equations. In this case, I'm going to choose the first equation, 2x plus y equals negative 2. I'm going to substitute this value of 4 in for the y. I'll just do that right underneath. 2x plus 4 equals negative 2. And I'm going to solve this equation for x. I'm going to subtract 4 from both sides to get 2x equals negative 6. Divide everything by 2 here, and I get x equals negative 3. And again, my solution is the same. It will always be the same in any method I choose, but that is my third and final method for solving a system of linear equations.